Recall that PCC was a more milder version of the chromic acid oxidation reaction, and it allowed us to stop at the aldehyde step instead of oxidizing a primary alcohol all the way to a carboxylic acid. The Swern oxidation is another mild form of oxidation that has gentle basic conditions instead of the strongly acidic conditions of the H2CrO4 reaction. So in this case, we would get the expected product, a ketone, from our secondary alcohol. We're actually going to use Dmso not as a solvent in this case, but as a reagent. It's going to react with oxalyl chloride, and we're going to use triethylamine as a base. And so the first step in this reaction, actually I want to intrigue you a little bit with the byproducts. So we're going to make dimethyl sulfide. It smells really bad, like a skunk. We're going to make CO2. We're going to make CO. And we're going to make two equivalents of HCl. And you see that's where we need the triethylamine, because we'll use the triethylamine to soak up the HCl, preventing our reaction conditions from becoming more acidic as the reaction proceeds. So the first step is Dmso reacting with oxalyl chloride. We're going to do a nucleophilic attack to form this intermediate. And then we're going to collapse that intermediate to form our reactive species. So the first thing we can do would be to lose chloride. So let's see, this is a nucleophilic attack. Then we have loss of the leaving group chloride to form this compound. And there is a plus on the sulfur, I should note that. So I have also one of the chloride byproducts. And then we can actually take that chloride byproduct and do sort of a substitution reaction. So here we have nucleophilic attack. And now we're forming the CO2 and the CO and another chloride. So we know that chloride is a good leaving group, and it stands to reason that anytime we form a gas, that could be a good leaving group too. So CO2 and CO are both good leaving groups. So we're breaking this CC bond here and forming a lone pair on the CO, right? This CO right here, that creates the carbon monoxide, and then this part creates the carbon dioxide. And so we get nucleophilic attack, and then here we're getting loss of leaving group, actually several leaving groups. And that ends up with this species here. We just made CO2, we just made CO, and we just made chloride. There's nothing there. So you see that we've made three excellent leaving groups, chloride and the two gases CO and CO2. And now we have this reactive intermediate that can react with our alcohol. So let's go back and treat our alcohol with our new species. You could call that a chloro-dimethyl-sulfonium ion if you wanted to. So what's going to happen here, of course, is we have a good leaving group and we have an okay nucleophile. We can draw a nucleophilic attack, loss of leaving group, just like we might draw with an SN2. Because the sulfur is bigger than a carbon, it is better suited for this nucleophilic attack, even with a poor nucleophile. And so that gets us to this compound. And of course, here's when the triethylamine comes into play. We're going to use the lone pair on the nitrogen to grab the hydrogen to quickly quench this dication. I hope you're a little uneasy about these two cations that are next to each other. But the driving force, again, is the loss of these great leaving groups up here. So those are helping push this reaction forward, even though we just produced briefly a rather poor dication compound. And then we can take another equivalent of triethylamine. Because that sulfur is a cation, it actually makes the adjacent hydrogen somewhat acidic. And we can produce this neutral intermediate. And actually, I would rather make that a negative charge on the outside there. So let's erase this. I'm going to take this arrow and I'm going to put the charge on the carbon, not on the bond. Okay. And so finally, we know that all oxidations at some point have to involve the hydrogen that's on the carbon bearing the O. We need to lose that hydrogen, we need to form a CO double bond, and so now our molecule is well suited to do that. We can take the C minus, grab the what we might call the carbon or the hydrogen on the carbon bearing the O. That can be used to form the pi bond, and then we can lose dimethyl sulfide. So I've just created this pi bond with that long loopy arrow right there, and I've also just created this neutral molecule with this arrow. I'm putting another lone pair on the sulfur and creating a neutral dimethyl sulfur molecule. And so here I have my carbonyl. After all that, you can see that the byproducts up here are many. That is one of the drawbacks of the Swern reaction. It is not very green. It creates many, many atoms and many molecules as byproducts. And really, our goal is simply to remove 2 hydrogens off of our starting material, alcohol. In order to remove those 2 H's, we create several gases, some strong acid, and a really nasty smelling dimethyl sulfide molecule. But nonetheless, that is the Swern oxidation. It is useful because it is not under acidic conditions, and it can be used to take primary alcohols and oxidize them only to the aldehyde functional group. So you could write Swern. It's probably better to write out all of the ingredients: Dmso, oxalyl chloride, and triethylamine. And so this is the Swern oxidation. Again, it's milder conditions than the standard Jones reagent or the H2CrO4. And it can be used similarly to PCC, but it has different benefits, mostly because it's not an acidic environment. Here's an example of where this Swern oxidation might be useful. You can see here that we have a primary alcohol. We also have several alkenes that, as we learned from Organic 1, when we're in acidic conditions, we might add water across the alkene. And so the Swern prevents those acidic conditions from occurring. And so the only product we'd expect here would be the aldehyde product. The alkenes are preserved. They are not reacted. They do not undergo an addition reaction. Also, we do not produce the carboxylic acid. So, several pluses to this Swern oxidation. If we wanted to do the same thing, and maybe we wanted the carboxylic acid, for instance, or we just wanted to try to get to the aldehyde, and we used H2CrO4, we would expect many products. Certainly the carboxylic acid would be a product. We could also hydrate, add water across one or both of these double bonds and end up with a couple of different types of alcohols. And so we get a whole mess of things, whereas with the Swern oxidation, we have a nice, well-controlled, mild reaction.